students, the next question is more realistic towards a motor or a generator in which we have a magnetic core and we have a rotating part. So for example, a typical motor has a rotor and it also has a stationary part, stator. So the rotating part has, and there we have a magnetic core. So the rotating part has to rotate, and if there is no air gap, this rotating part cannot rotate. So we have a stator and we have a rotor. Both are made up of ferromagnetic substances, and the magnetic flux is flowing through the air gap into the rotor to produce all the effects of torque and other, if voltages are getting induced, currents are flowing, everything. So the core resembles a real motor system, and mean path length they have given, that is 50 centimeter, and cross sectional area is also given, that is 12 centimeter. This is the mean path length. Rotor, the mean path length for the rotor they have given is 5 centimeter, and they have given the length of the air gaps also, and the cross sectional area of each air gap is 14 centimeters square. Okay, so area of the core they have given is 12 centimeters square, and after fringing the area for the air gaps is 14 centimeters square. The iron of the core has a permeability. They have given the relative permeability, that is equals to 2000, and the number of turns are also given, 200. And what it is trying to, what is the main question is, if the current in the wire is adjusted to 1 ampere, so if I equals to 1 ampere, what will be the flux density through these air gaps? And the flux density through the air gap will be total flux divided by area of the air gap. So the first and the foremost step should be that we should be able to draw the equivalent magnetic circuit. So one way to look at this core, and that will simplify this system, will be, we can, if we look at the side view of the core is actually like this. And this is the stator part and that is the rotor part. So actually what we can see from here is that okay, this length is 50 centimeter, and this is actually one reluctance, RC. Then this length they have also given you, this is a reluctance of the rotor. Now this is, and this, there are two air gaps here. I call this A1 and I call this A2. So actually there is a reluctance A1 also, and there is a reluctance A2 also. So the total reluctance we can calculate from this. If we are able to calculate the total reluctance, we will be able, we have N and I, we will be able to calculate F equals to, we can calculate F. If we have RT, we will be able to calculate the flux. Once we have the flux, we will be able to calculate flux density that is required in the question. So the equivalent magnetic circuit for this circuit will become, we have one source and we have four types of reluctances. So let's call this stator because core is there and rotor is also there. Then we have our AG1 for the air gap 1. Then we have the reluctance of the rotor, and then we have the reluctance of the air gap 2. And here we have F equals to Ni. We have the value of N and I also. If we are able to calculate this flux, we will be able to calculate the flux density through the air gaps. So I hope the rest is not that complex. Rest all the students knows the basic formulas. And so let's look at this. What will be R stator? R stator will be length of stator divided by mu and area of the stator. Length of the stator they have already given to us, that is 50 centimeter, that is 0.5 meters. Mu we know is equals to mu naught into mu r. So because the relative permeability is 2000, so we will have 4 pi into 10 raised to power minus 7 and 2000. And what about the area of cross section for the core? Here it is 12 into 10 raised to power minus 4. So the value of RS will become RS equals to, and here you must be very careful when you are calculating these values. Again, I am warning because a lot of students make mistake while calculating these values. So this is the value of stator resistance. The next is, let's calculate for the rotor. Which is the rotor part? This is the rotor. So for rotor, it will be length of rotor over, again it is made up of same core, mu r, and the area of cross section for the rotor, it is same as the core, so it will be the same area, that is actually area of rotor. And here if you can see, in reality students you have to perform all the calculations, but to keep the duration of the video short, so length of the rotor it is given and it is 5 centimeter, that is 0.05 meter. Mu naught and mu r you know. Area of the rotor again is 12 into 10 raised to power minus 4 meter square. So the value for the rotor will become, so the value for our rotor impedance will be 16,600 ampere turns per Weber. So we have calculated the rotor, we have calculated the stator. Now about the air gaps. So for the air gap, we have length of the air gap divided by, again it is a air gap, relative permeability will be 0, and air gap they have given the area for the air gap, it is 14 centimeter square. So we can see length of the air gap is 0.0005 meters, as it was 0.05 centimeters, and area gap is 14 into 10 raised to power minus 4 meters square. Mu naught we know the value. And so what we will have for the air gap, for this is actually for one air gap, 284,000 ampere turns per Weber. Can you look at this? Can you appreciate the reality that such a small air gap, and this is for one air gap, we have two air gaps, and they will add, they will be actually two reluctances like this, and look at the reluctances of the core, such a long core, and there's a huge difference. That is because of the permeability. So R equivalent can be calculated as RS plus RR plus RAG1 plus RAG2. This is actually AG1 and AG2 is same as that one. So the R equivalent value will be 7,000 ampere turns per Weber. Now once you have this value, And we also have the value of F, that is equals to Ni, and it is we have the number of turns are 200 turns and the current is 1 ampere. So 200 turns into 1 ampere, that will be equals to F equals to 200 ampere turns. Now we have to calculate, as I told you, what was the main question? Resulting flux density. To calculate the flux density in the air gap, we have to calculate the flux. Flux we can calculate very easily because we have all the necessary values. So we know that F equals to RT. So the flux total is F over RT, and that will become 200 divided by our total 000. So the flux of T will be actually 0.00266 Webers. That is actually 2.66 milliwebers. Now we have this, and we have to calculate flux density. Flux density in the air gaps. So this can be now easily calculated, and the flux density through the air gap will be air gap is equal to flux total divided by area of the air gap, and the flux total is 2.66 milliweber, and the area of the air gap including the fringing was 14 into 10 raised to power minus 4 meters square. So the value of the flux density will become B equals to 0.19 Tesla. So this is the actual flux density that will be flowing through the air gaps for this rotor. I hope it helps. Thank you.